My name is Qiang from Zhejiang University and EPFL. I'm visiting EPFL now. Then that will be a postdoc in September. I'm very glad to be here in the last session to introduce our recent fuzzing work on virtual device, VIDEZZO, dependency-aware virtual device fuzzing. This is a joint work with Flavio, Yajin, and Mathias from Zhejiang University and EPFL. So what is a virtual device? I'm going to say virtual device security really matters, but first question is what is a virtual device? A virtual device is a piece of software that emulates hardware. If you are using VirtualBox or QEMU, the virtual audio card, virtual network card, they are virtual devices. Virtual devices are part of the virtualization technology. When we are talking about the virtualization, we don't want to forget the isolation. Hypervisor is the core of the virtualization. It tries to isolate the guest OS from the host. However, this assumption is not usually guaranteed due to some high-impact vulnerabilities like Venom that makes an attacker can escape from a virtual machine, then take over the whole host infrastructure. Virtual device vulnerabilities are the main attack surface and the main biggest attack type that we should care about. Near half of the QEMU vulnerabilities and the VM escapes are in virtual devices. If we could found these vulnerabilities in advance and fix them in advance, that would benefit a lot. Since fuzzing has been very successful in looking for bugs, so the question we are going to answer today is how to fuzz virtual device in an efficient and scalable way. Here are some key points I would like to say in advance, so you understand more of my work. First of all is the virtual device message. A virtual device is interact with operating system with virtual device message. They are not limited to, but in this context, MMO, read and write, PIO, port IO, read and write, and DMA, read and write operations. One more thing about a virtual device message is a message will have fields inside. Several messages will form a message sequence which explicitly implies that a message has order. I have an example here. There are two MMO messages. Each message has three fields. The first one, register, is the register offside in a virtual device. The virtual device will parse it and goes to different branches. Then command and pointer are data embedded into the messages that will be passed later. Based on these two concepts, we identify two new key challenges to fuzz virtual devices, intra-message dependency and inter-message dependency. I'm going to introduce these dependencies, what they are, and how to address them in the following. The first challenge is the intra-message dependency. A field in a virtual device message may be dependent on another field. Here is an example. This is message 1, where a pointer field will point to different object. During the fuzzing, we want to know which object exactly the pointer will point to. And it turns out that which object it will point to, it's depending on the value of the command message. The lower 3 bits of command really matter. If the value is 1, the pointer will point to object 1. If the value is 2, the pointer will point to object 2. The second challenge is the inter-message dependency. A message may be dependent on a previously issued message. We have message 2 and message 3 here, as you can see. They operate two different registers, 0 and 4. So the question is, which message should be issued issued first during fuzzing. And it turns out that message 3 should be issued later after message 2 because of a shared variable A. Message 2 that operates on register 0 will first define it, make it non-zero. Then message 3 that operates on register 4 can take the value, check the value, then continue its execution, more functionality. So here we are. To address the intra-message dependency, we propose the inter-message annotation. The idea is we are looking at the source code of virtual devices and see a lot of semantics information there, so we want to automatically extract such information from the source code. We use a CodeQL we develop a CodeQL script to analyze the QEMU virtual device source code to automatically generate the intra-message dependency. I will show you later. But still, some limited manual effort is necessary. The limit I will show you later. Then, with the extracted annotation, we can generate messages with intra-message dependency automatically with some Python scripts or whatever scripts. So the intra-message annotation looks like this. You can see from the line 0 to line 5, I think, it has a small type system where that defines the field size, and the field type inside the message. For the following lines use an API to define the real dependency, like just to address the problem I posted before, which object should point to which object. In summary, we semi-automatically extract the intra-message dependency from the source code. To address the inter-message dependency, we would like to be automatic as well. So the idea is we take a message sequence, then we mutate it, and if the mutated message introduces any new coverage, we will take into the consideration and put it into the corpus. Then we design 3 levels of mutators: message level, sequence level, and group level mutators. They means very straightforward. Message level mutators will operate on a field inside the message. Sequence level mutators will operate on several messages. The group message mutator will put some related message together and make them intact during the following fuzzing. So they should be close. These messages should be close. So in summary, we would like to let the fuzzer automatically learn the inter-message dependency during fuzzing. Here is the fuzzing workflow that I can use to show you how we combine these technology. Suppose we have 4 messages, 1, 2, 3, 4. Then we apply some mutators like change value, erase message, in the repeated message. Then we will get new for not all new a mutated message, a test case. Each message in the test case will be dispatched into the virtual device under test. Here we are. One more thing that is very interesting is the message 4. There is a very little flag there. The message 4 will tell the fuzzer that the virtual device under test is going to load some data from the DMA buffer. So message 5 and message 6 then automatically generated by the intra-message annotation to set up the buffer and the content of the buffer. Fuse, pointer, flags, whatever inside. Finally, if the sequence really introduces any new coverage, it will be put it into the corpus. One last step here is for the M5, message 5, message 6, and message 4, we will put them together. We will group them together and make the fuzzer know, okay, they are grouped, and don't let them be apart. Okay, some evaluation results are here. Recalling that we are extracting intra-message annotation from the source code, VIDEZZO managed to model 18 QEMU virtual devices, while one of our related work, NICS, models only one at that time manually. The question will be, why do we need manual efforts? I would say it's because of the code complexity of the virtual device. We summarize 3 main reasons: name type, disjointed control flow, and context-aware dependency. But I'm not going to introduce the details here. If you please refer to our paper. The argument I want to make here is not all virtual devices need manual effort. These corner cases only cover limited virtual devices. So if we would like to support a new virtual devices, high probability, it's OK. VIDEZZO scales to 28 virtual devices, covering 5 device categories, 4 architectures, and 2 hypervisors. We cover QEMU and the VirtualBox. It achieves competitive coverage, final coverage faster, as you can see from the figure. Green line is VIDEZZO. The coverage first rapidly goes up during the 10 seconds, then levels out within 1 hour, which is pretty good. VIDEZZO discovers 24 existing bugs and 28 new bugs in both QEMU and VirtualBox, in both VirtIO devices and non-VirtIO devices. For the bug types, it covers not only the assertion failures and aborts, but also spatial and temporal memory corruptions. We are also very active to join the community, so we have provided several patches accepted by the QEMU community. So here we are some takeaways. Fuzzing virtual devices must consider the intra-message dependency and inter-message dependency. VIDEZZO addresses these challenges with intra-message annotation and inter-message mutators. VIDEZZO found 28 new bugs, and in both QEMU and VirtualBox with 1 CVE design. If you are interested into the detail, please scan the QR code. You can find our paper. Thank you. That's all. I'd like to take any question from you.
Excellent.
Thank you.
Questions for our speaker? Please don't be shy. I can stare at you for a long time. It's just like class. Come right up to the microphone, ask your burning questions about finding bugs in virtual devices. So I guess I will ask a question. Yep. Very cool work. It made me wonder, so it seems that there's other fuzzing targets that also have the problems of, let's say, message dependencies or sequence dependencies.
Yes.
Like, I think syscalls maybe come to mind. Have
Yes.
you thought about applying, are similar types of techniques, can they be applied to other fuzzing targets?
Yes, I would say, yes, I also consider this. First of all, I have to say so the technique we use, the inter-message mutators, are pretty new, that nobody uses it in fuzzing virtual devices. So I think that this is necessary to do the first implementation and trial. Some differences are there between MMO, so these messages, and syscalls. Like each syscall has a specific meaning, like read and write, close, whatever. But each MMO is just a register with some random data. You don't know what happens there. I believe, I know a paper named Moonshine. It collects the syscall trees and try to find interesting patterns. I think this is also used in another paper, Mondo Fuzz, accepted in Usenix this year, I think. I would say, so overall, I think our methodology is necessary, and then I think there will be opportunities to leverage the domain knowledge from the syscalls, yes.
Excellent, thank you. All right, name and affiliation, please.
Hi, I'm Kelly Keotis from Trailer Bits,
Yep.
and I think this was an awesome paper.
Thank you.
So have you considered using this work for detecting data races? Was all I wondered.
Very good question. I've been always thinking about it, but we haven't had a try. Yeah, because you can actually issue 2 close MMO operations in practice, and when you are issuing the second MMO, you cannot guarantee the first one is finished. I think this is a quite interesting problem, and I'm going to look at it. Yeah, we can discuss it later, but I have no solution. Yeah.
Yeah, I'll find you after. Thank you.
Yeah, thank you.
Awesome. Let's thank our speaker one more time.
Yeah, thank you very much.